shorter talks in this session. I will begin with Alessandro Morbidelli to tell us about asteroids formed big.
Thank you. So it's not very nice for an organizer to be also a speaker, but I thought that I take half an hour to bring to your attention this work that we did, because it could trigger discussions on the formation of planetesimals, and as we saw before, it triggered discussion even before I presented. So, so I think we all agree that planet formation takes 3 steps. There is the first step is planetesimal formation, that we don't understand very well. It's what we debate here. Then there is some step of where some collisional coagulation takes place, and through the well-known processes of runaway growth and oligarchic growth, this leads to the formation of planetary embryos and planetary cores. And then in the first step, what happens depends on the environment. In the outer solar system, we have the accretion of gas around some of the cores, which leads to the giant planets. Here we had a phase of high velocity collision between embryos that led to the formation of the terrestrial planets. And in other regions, we have a phase of dynamical excitation and mass loss due to dynamical ejection and collisional erosion. And this is what happened in the asteroid belt and in the Kuiper belts. So here I will focus on the asteroid belt. And the reason is that this phase of dynamical excitation and mass loss, I think, is quite well modeled now, and I will say a few words about that just in a minute. And so thanks to that, starting from the current size frequency distribution of asteroids and other constraints from the asteroid belt, and having this model of collisional and dynamical erosion, we can work out what was the size frequency distribution of the asteroid belt at the end of this collisional coagulation phase. That's quite of a confidence, I would say. The collisional coagulation phase can be simulated using statistical coagulation codes, the kind of codes the STU is using or Scott Kenyon is using, and we did our own coagulation code, nothing fancy, just code that should be able to reproduce what Kenyon and STU are doing. So given that we know the end result and having a code that reproduces this process, we can try to work out what had to be the initial conditions at the beginning of step 2 in order to get the size frequency distribution that we need at the end of step 2. But the initial conditions at the end of step 2 are nothing else than the end result, the end product of step 1. So the goal of all this work is to try to infer from the asteroid belt some information, deduce some information on what had to be the size distribution of the planetesimals in the asteroid belt region when they formed, whatever their formation process, and therefore give some positive information, feedback, and constraint to people that work on planetesimal formation model. This is not a planetesimal formation model study, it's a backward study in order to deduce constraints on planetesimal formation. So this is the logic of our study. So what are the main belt constraints, and what do we think was the size frequency distribution of the main belt before dynamical excitation and mass loss started? This is the current size frequency distribution, and let's say it's complete observationally down to 10-15 kilometers. So don't worry about biases. What you see here, these bumps are real. In particular, this bump at 100 kilometers is real. It's not due to observational biases. So Botke et al. In 2005 studied the collisional evolution of the asteroid belt through 4.5 billion years since the asteroids acquired their current orbital excitation. And they used many asteroid constraints like the number of asteroid families, the number of basins of Vesta, the preservation of the basaltic crust on Vesta, and so on and so forth, and concluded that, yeah, collisional evolution was important, but not heavy enough to modify substantially the slope of the size frequency distribution that you observe for the asteroids now between 100 and 1,000 kilometers. So this slope is primordial in the sense that was there already at the end of step 2. The same is for this bump. Botke et al. Argued and I think demonstrated that this bump could not have been produced by collisions. That is, it's not possible that the size frequency distribution at the end of step 2 was like this, and 4.5 billion years of collisions brought this size distribution like that. Because if you want to do this, you need the asteroids are too weak, then you would produce too many families, you would produce too many basins of Vesta, and so on and so forth. So Botke et al. Concluded that this bump was there from the beginning. They could not say whether this size distribution was there from the end of step 2. It might be that the size distribution at the end of step 2 was much flatter, and then it steepened up because of the production of fragments from the few breakups that occurred in the 100,000 kilometers regime. So I would say we have some unconstrained feature here, but the bump had to be there. The current asteroid belt has very little mass, less than 0.1% of the mass that we think was there at the beginning. Since 85, the group of Don Davis, Stu Wiley, and Schilling, it was demonstrated that this mass was not lost by collision, but must have been lost mostly by dynamical ejection. So dynamical ejection is essentially size-independent process. So if we are missing a factor of 1,000 in the mass, it means that at some point the size distribution was like the one I just sketched, but scaled up by a factor of 1,000 with respect to current. And the best model to explain the asteroid excitation and the depletion, the ejection of 99.9% of the asteroid is a model proposed by George Wedderl in '92. And this model assumes that in the asteroid belt, the largest objects were not series size, but they were real planetary embryos, something with a mass of the order of the lunar mass or Martian mass, so in that size range. So that's our understanding. So we think that at the end of step 2, the size frequency distribution had to come somewhere in between these two lines, match with this line, and then end up here. And this is what we want to reproduce with our statistical coagulation code. So traditionally, people think that, well, nature somehow was able to overcome the meter size barrier and produce 1 kilometer planetesimals. So that in the beginning, in the asteroid belt, we might have had some 1.5 Earth masses of kilometer-sized planetesimals. And then collisional coagulation, binary coagulation took place. And so this is the final size frequency distribution that we would obtain with our code. So some successes, we do produce the embryos that we need. Some insuccesses, we have a deficit of about an order of magnitude in the number of large asteroids that we produce. Now you could say, okay, well, you've put here a factor of 1,000. You don't really know. Maybe it's just a factor of 100. Okay, let's put a factor of 100. Then the size frequency distribution match decently. But as you can see, and Stu showed that before as well, there is no sign of a bump around 100 kilometers. So we can't reproduce the bump. Even if you deplete 99% of the asteroids, so to bring this down to one series, at the end you have too much mass to be eliminated by collisions, more than you can. You have too many 10-kilometer projectiles on Vesta, so you will form more than one basin. So this kind of size frequency distribution does not satisfy the constraints that we have from the asteroid belt. And we have tried with many different parameters, changing the initial mass, extending the simulation time scale. This was 3 million years, we went to 10 million years, changing the Q star of the asteroids. The results are always consistent with this kind of result. Here, we have no external stirring. The velocities among the asteroids are stirred up by close encounters. But we know that there is some level of turbulence in the disks. So turbulence creates density fluctuations in the gas. And these density fluctuations act like mass scatterers. So that's why we call it a sort of turbulence scattering that enhances the eccentricities of planetesimals of every size. And this is something, for instance, that Richard Nelson pointed out very well in 2005. So we in our group, and with Shigeru Ida and Greg Laughlin and Fred Adams, we tried to model this turbulent excitation of eccentricities through turbulence scattering through a symbol model which is calibrated on MRI simulations. So the evolution of the eccentricity is proportional to F, which is the density in minimum mass solar nebula scale, times a parameter gamma that Stu mentioned this morning. So for instance, for gamma of 10 to minus 3, a planetesimal eccentricity would behave like that. Now you might wonder how gamma scales with alpha, and there is a very interesting new work by Clément Baruteau who shows that alpha is proportional to gamma squared and divided by the aspect ratio squared, and that for a 3% aspect ratio, gamma of 10 to minus 4 correspond to an alpha of phi 10 to minus 4. And this has been measured on hydrodynamical simulations by imposing these stochastic fluctuations with a magnitude gamma and measuring what is the transport coefficient in the disk, which is initially inviscid. Now, if I take my 1 kilometer planetesimals and I assume that I have a small gamma in 2 10 to minus 4, which would give an alpha of 2 10 to minus 3, that's what I get. I get no accretion at all because the velocity dispersion is too high, and essentially my 1 kilometer planetesimal, when they hit, they break. And here I have very high Q star. I mean, Zoe would scream at my Q star because it's too strong. And even with that Q star, I get no accretion at all.
So what are the relative velocities between these?
That's a good question. So this is a plot that comes from another paper that Shigeru, Tristan Guillaume, myself published in FJ 1 year ago. So this shows the equilibrium eccentricity of planetesimals as a function of their size, equilibrium between turbulent stirring, this computed for 10 to minus 3, gamma 10 to minus 3, gas drag or collisional damping. Okay, this is the collisional equilibrium eccentricity. And this is the eccentricity that would correspond to a velocity, relative velocity equal to the escape velocity from the bodies of that size. So we are here. And so for gamma 10 to minus 3, we have an eccentricity of a few times 10 to minus 3. For a gamma of 2 10 to minus 4, essentially is 5 times smaller. So we are somewhere here, and the escape velocity would correspond to an eccentricity much lower. So essentially, we have to decrease gamma to about 2 10 to minus 5 in order to have accretion keep going like before, like if nothing happened, and we check that in our code. Now, Stu this morning showed that you can get this bump at 100 kilometers starting from 100 meters planetesimals. And as he said, there his disk was initially very cold, and the initial velocity dispersion was equal to the escape velocities from these 100-meter bodies. So something of the order of 5 centimeters per second. But if you put in some turbulence, you would expect the eccentricity to be much larger and compared to the escape velocity. So essentially, you have, instead of having an eccentricity of 10 to minus 3 that you get with gamma 10 to minus 3, you have to have an eccentricity of the order of 10 to minus 6. So you have to decrease gamma by 3 orders of magnitude. So have a gamma of the order of 2 times 10 to minus 6, which would correspond over to an alpha of 2 times 10 to minus 7. So yesterday we heard talks even by Caroline about the dead zone. She was speaking about alpha of 10 to minus 3, 10 to minus 4, not to speak about baroclinic instability, Kelvin-Helmholtz instability. So I think really one has to assume an unrealistic quiet turbulence, and as soon as one introduces a little bit of turbulence stirring, collision starting from 100-meter planetesimal or 1 kilometer planetesimal simply stalls. So if we can't reproduce the bump starting from small sizes or even smaller sizes, what about starting from larger sizes? So we've been inspired by these new models by Jeff and Johansen and Klar and Udin, that maybe planetesimals form big because of concentration of a large amount of small solids in turbulent structures of the disk. So we said, okay, let's see what is the effect of coagulation if you start from large planetesimals. So given that the bump is observed at 100 kilometers, just let's try at the beginning to have initially all planetesimals at 100 kilometers, not that we think that all planetesimals are exactly the size of 100 kilometers, just to see what the effect of the initial size is. And sure enough, as Stu showed this morning, we get this bump, very clear bump. The size distribution we get is steeper than the one that we observe in the asteroid belt, and we fail to produce large embryos, in agreement with what Stu showed. So our codes are in pretty good agreement with each other, which is good. This simulation is simplistic though, because we only have 100 kilometer planetesimals, no turbulence, nothing else. But these models that produce large planetesimals need very small stuff to start with, chondrule-sized particles or meter-sized boulders. We will hear talks about these models later these days, and we don't have them here. So we have tried to make the model a little bit more sophisticated or realistic. So we have a setup that we call the case A, where at the beginning all the mass, so 1.5 Earth masses, in small particles, And every time we introduce a 100-kilometer planetesimal by hand, we subtract a number of small bodies for the same equivalent mass. Okay. And if you do that, the size distribution changes dramatically with respect to what we had before. Why? Because now the first big planetesimals that I introduce them in a disk, massive disk, of small boulders. So there is an amazing, effective, dramatic runaway growth going on, and this produces this size distribution and leads to embryos which are well above the mass of Mars. And it doesn't matter what is the prescription for our small particles. We can assume they are perfectly coupled with the gas. We can assume that they are meter-sized boulders that drift radially. More or less, the size distribution is the same. We have a huge runaway growth.
What is the surface density profile
Of what?
of your distribution of the
Oh, it's a narrow annulus, as large as the asteroid belt. So there is no profile. Then we can say, well, okay, let's try something different. Let's introduce in time for, I think we introduced stuff for over 500,000 years. Every time we introduce a 100-kilometer planetesimal, we introduce also boulders for the same total mass. The rationale for this is essentially that the formation of your big planetesimals is regulated by the availability of the building blocks. In other words, you can't form an asteroid without forming the chondrules first. So in this and so you introduce small particles and big planetesimals together. It's about the same, because the big bodies see the small bodies around them. There is a very high runaway growth, so the size distribution that we get at the end is very, very different from that of the asteroids, even if we have the bump at 100 kilometers. You may say, okay, so this runaway growth is not what we want. Maybe playing with turbulence stirring, we can stop this runaway growth and have a more gradual growth with a shallower distribution. And so we tried various turbulent excitations and never worked. It's either turbulence is too strong and then we abort accretion, or it's too weak and we still have a runaway. And it's very hard, if not impossible, to find some value of gamma that kills the runaway growth but still promotes accretion. And the reason for that is easy to understand if you think about it. That, okay, if turbulence is too big, we don't have accretion. It's too weak, it's negligible. Imagine you tune it so that the dispersion velocity is of the order of the escape velocity from 100 kilometers planetesimal. So you have no focusing, no runaway. Okay. So initially accretion starts in an ordered way, but then you produce bigger planetesimals. And the turbulence stirring is size independent. So these bigger planetesimals that I produce will have an escape velocity larger than the turbulence stirring, and then runaway will start. So we never succeeded in finding a turbulent parameter that promotes accretion and that does not allow runaway growth. So if from 100-kilometer planetesimals alone, or a narrow distribution around 100-kilometer planetesimals, we can get at the end a size distribution analog to that of the asteroid belt. So we said, well, let's put in a range. So from 100 kilometers, for instance, to 500 kilometers. With what size distribution? Well, let's try the size distribution that we see. So this is our initial condition with dots. And this is what we get at the end. Again, in a simple simulations where we only have the large planetesimals, no turbulence stirring, no small particles. So very simplistic, it works pretty well. This is the size distribution in the asteroid belt now. This is a sort of error bar, what could have been at the beginning, given that we then select dynamically one asteroid out of 1,000. If we introduce the small bodies, either the case A setup or case B setup, it doesn't matter. Again, runaway growth, so we introduce a break at the size of the largest planetesimals we introduce in the system. So it doesn't match very well the asteroid belt anymore. It could still be okay, because after all, this point is carried by one asteroid, Vesta. So if Ceres. If Ceres has been very lucky to survive in the asteroid belt, even if by probability argument it shouldn't, we might be misled, of course. And the turbulence, again, doesn't help. Now with a turbulence gamma of 2 × 10⁻⁴, which was preventing accretion in the 1 kilometer, 100 kilometer case, now we can have runaway growth. That's because we start with planetesimals as large as 500 kilometers. And if we increase the gamma by a factor of 10, then we abort accretion. And in no case we can get something without a break here at 500 kilometers. So not to have the break there, we need that the size of the largest planetesimals was larger. So we tried another case with the planetesimals spanning from 100 to 1,000 kilometers. Size distribution is indicated by these black dots, a little bit shallower than what is the current size distribution of the asteroid belt. Then let the system go, and you see the size distribution is more or less preserved. So you start from the current one and you get the current one. The bump at 100 kilometers is there because we have nothing below, and we produce some sort of lunar mass embryos. This is again a simple simulations with only big planetesimals, no turbulence scattering, no small bodies. But if we introduce the small bodies, yeah, we start to have some runaway growth with a break in the size distribution here. But given that at the end we only select dynamical ejection, we select only asteroids smaller than 1,000 kilometers. We don't know what was the size distribution about here, and we have bigger embryos. And if introduce turbulent scattering, it still works very well, even for quite a strong turbulence, because we have large planetesimals to start with. So our conclusion is that to match the current size frequency distribution in the asteroid belt and the size frequency distribution that we thought the asteroid belt had at the time of its global dynamical excitation, we need to start with large planetesimals. How large is large? So the bump at 100 kilometers suggests that the initial size frequency distribution had a sort of minimal size at 100 kilometers. I'm not saying that 70 kilometers asteroid planetesimal did not exist, of course, but that was a sort of minimal predominant size. And how big they had to be? We have failed to reproduce the size distribution of the asteroid belt just with 100 kilometers or few hundred kilometers planetesimals. We always produce a break in the size distribution at the size of the largest asteroids. And given that we don't see that break, this suggests to us that the initial planetesimals spanned the size range from 100 kilometers, the bump size, up to Ceres size, or beyond, for what we know, we don't know. And the current size distribution in the 100 and 1,000 kilometers range, which has not been affected by 4.5 billion years of collisional grinding, was not affected by collisional coagulation either. So the modelers for the planetesimal formation can use that size frequency distribution as a sort of target size frequency distribution in their models. And so this is a new set of constraints and challenges for the planetesimal formation models that we will hear more today and tomorrow. So collisional coagulation, if all this is true, played only a minor role in the asteroid belt accretion. And maybe the only role it played was to form the embryos from which terrestrial planets formed and the asteroid belt was excited, starting from a population of about 4,000 Ceres-sized bodies. And we've seen that if these planetesimals form big, but there are still a lot of small boulders or chondrule-sized particles or whatever carrying a significant mass, this triggers an amazing, very efficient, terrifically efficient runaway growth. And so this opens a new hope to form the cores of the giant planets. We still don't understand how the cores of the giant planets formed, because runaway growth tends to stall too early, and maybe starting from a disk which is totally bimodal, with big planetesimals formed big by some gravitational instability, collective mass, collective gravity effect, in a sea of small particles, can bring runaway growth much further than we would starting from classical size distribution models. Although it's not clear that we can go up to 10 Earth masses, the size of the core of Jupiter or Saturn. So I'm going to stop here, take your questions.
For your initial 4.2 billion years ago or whatever distribution of asteroids, do you account for the fact that, first of all, Vesta is close in, away from most of the asteroids, and secondly, that Yarkovsky might get rid of some of the asteroids in the region which could, size range that could damage Vesta, so that it might not be a purely,
Mm-hmm.
purely, 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 size independent.
Yeah, so your question does not concern this recent work, concerns more the Botke et al. Work that we use
Right.
at the beginning to infer properties of the asteroid belt.
Yeah.
And so the position of Vesta in the asteroid belt and its collision probability with the rest is taken into account. Yarkovsky was not taken into account, but the size of a projectile forming the basin of Vesta is about 30 kilometers. So you don't expect Yarkovsky to deplete the asteroid belt of 30 kilometers projectiles. Right? So the big constraint is that, well, there is this surface basaltic crust on Vesta, which you need to preserve. And then it's a number of big basins. So essentially there is one big basin on Vesta, which was formed by a 30-kilometer projectile. There is one, not five, not zero, right? And so you need, this gives a constraint on the number of projectiles of a few tens of kilometers in size, as Stu said this morning, and you can't really reuse that by Yarkovsky.
Yeah. How do you fit the eccentricity of the asteroid you produce with your slope? Because in parallel to the size distribution,
Sure. No.
the velocity
Okay.
dispersion.
Sure, of course. The collisional coagulation phase gives a velocity dispersion, which is tiny compared to what we observe. But then you have the dynamical excitation event, which is driven by the embryos. And this ejects 99% to 99.9% of the asteroids and gives the current orbital dispersion of the asteroid belt. And this is a step which has been modeled using dynamical codes very well, starting from Wetherill with his Monte Carlo codes, and then Chambers, and myself and O'Brien, and Sean Raymond, and so on. So it's not self-stirring that gives the current eccentricity excitation of the asteroid belt. It's a global instability event triggered by the formation of the embryos that does it.
Yes, but my question is, do you fit the eccentricity of the bodies?
No, we don't need to. Because we know that the current eccentricities of the asteroid will come later during terrestrial planet formation, when the embryos that were formed everywhere in the inner solar system become unstable when the gas goes away and Jupiter forms. So that's what gives the current dynamical structure of the asteroid belt. So we don't need to fit for the dynamical structure of the asteroid belt during the collisional coagulation process. That's in step 3, not in step 2.
You do include viscous stirring.
We do include stirring, but we don't have a target. Our target, let's go back here. Oops. Okay, so we have 3 steps. The current dynamical excitation of the belt is acquired here. It's not acquired here. So we have self-stirring, of course, in the statistical coagulation process, like Stu or Scott had, but we don't have to match at this point the current dynamical excitation of the belt, because the current dynamical excitation of the belt is acquired here and not here.
Alessandro?
Morbi, I would like to bring up another aspect that you never mentioned, and this is the dusty end of the size distribution. So you mentioned you extend all your plots further to the left, okay, and you
Sure.
think of what is the amount of dust that is produced, and what you are doing using the size distribution of the present-day asteroid belt is, of course, quite a natural and reasonable thing. But I just would like to point out that there might be another group of constraints coming from debris disks. So I think we believe that planetesimals formed more or less in the same way in the solar system, and at least around other solar type stars. And so what I tried to do actually, after I heard your talk half a year ago, I tried to run our collisional code to look at dust production. And the result is, if you only consider the planetesimals in the region between 100 kilometers and 1,000, and no small objects at all, it takes way too long for such a disk to start really producing dust at fractional luminosities observed. You said the point, so you do need small projectiles, and I think if you use a reasonable flatter slope below 100 kilometers, it might work. But the point that I would like to make, that you can even obtain further constraints on the projectiles, on the objects smaller than 100 kilometers, from comparison with debris disks. We know that at, let's say, 100 mega years, the debris disks are quite luminous. The fractional luminosity is like 10 to the minus 3, minus 4. So this is another possibility for you to get an initial constraints.
Yeah, fair
I'll
enough.
show you some plots later. Actually.
Okay, yeah, when we assume that the size distribution is truncated at 100 kilometers, it's just by convenience, and I have nothing against size distribution going a little bit smaller, provided that there is some primordial bump. What you say, though, surprises me a little bit, because my conversations with Meyer in Zurich, was in Arizona before, he always claims that the hot dust in young systems disappear extremely quickly. And in a few million years, a few tens of million years. So she's looking actually for size distributions that don't produce much dust.
I'm not speaking of hot dust. I mean, just normal things that produce emission at, I don't know, 70 microns.
70 microns,
Yeah.
but this would be in the Kuiper belt, not in the asteroid belt.
Yeah, okay, so some amount of 24. Doesn't matter. But anyway, the point is that if you simply continue your plots to the left, well below 1 kilometer, let's say, or 100 meters, so you really go to dust.
Yeah, I understand your point.
Yeah.
But in terms of constraints, it's unclear to me if the asteroid belt seems to me, well, it seems to me that there is a deficit of hot dust in the young systems, which argues that the inner disk planetesimals are not very collisionally active. And this also matches our shock ages distribution in meteorites. There are almost no shock ages before the late heavy bombardment. And this kind of distribution would actually fit it. For the Kuiper belt, it may be different.
Morby, I should point out a difficulty with my model. It may also apply to yours. My model produced such rapid growth that one could be pretty sure that something the size of Ceres should have been melted into a puddle by Lumen 26 if it formed that quickly. I'm not sure if yours has that same problem. If you make Ceres-sized objects suddenly and initially, they would also melt unless you are able to do this over a period of millions of years, and that more or less coincidentally, Ceres was one of the last ones that was made.
I disagree. I think, as I said before in the discussion after his talk, it's availability of building blocks. You can't start to form asteroids before you form the chondrules. Now, I don't know why the chondrules formed 2 million years later after time zero, but they did. And so my time zero is essentially already t equal 2 million years. So even if I produce series at 2.1 million years, that it's okay. So this is not an answer. It's an empirical answer, if you want.
So you have to wait until you produce chondrules before you begin this process.
And until you have solid metal, you can build asteroids, I think. So, or if you do, maybe there is an earlier generation of chondrules and they went into planetesimals. Now you will call iron meteorites.
Well, if I wanted to invoke that, I suppose I could say that planetesimals, the 100-meter sized planetesimals, were prevented from forming for a couple of million years too. But we do have things that did form rapidly and melted, namely the parent bodies of the irons.
Yeah.
We have to account for them.
Yeah, but on one side, one criticizes these models because they form things too quickly, so everything should melt. On the other, so we say, okay, we start late, and then one says no, because there are planetesimals that are melted. So I really think it's the availability of building. It's a big problem. I'm not saying we have the answer, but for some reason, in the asteroid belt, the availability of building blocks, which are the chondrules, starts late, and maybe closer to the sun, it starts much earlier, and all the planetesimals that you form melted, and that's the iron meteorite parent bodies that have been injected in the asteroid belt later at stage 3.
Well, maybe Jeff will be able to tell us a little bit later whether his model can make things the size of Ceres as well as 100-kilometer bodies out of chondrules.
John.
If you have big bodies, when they collide,
If you have what? So
big bodies,
okay.
like what you're proposing, when they collide, their spin is very rapid in general.
Yeah.
And if you accrete a lot of small bodies, their
Yeah.
spin is
Yeah.
generally relatively small. what is the spin distribution?
Yeah. Thanks for this question. So Johansen and Lacerda just submitted, or they have a paper in press that they sent to me just before coming here, and where they studied essentially what happens in this stage. So when you have your planetesimals that form big, but they still are embedded in a sea of small particles. So they accrete a lot of small particles, and this triggers this runaway growth that I was showing. And they show that if these larger planetesimals, after being formed large, accrete still some 20 to 50% of their mass from the small bodies, you can explain why the biggest asteroids have an obliquity of 0 or 180 degrees and not 90. There is a deficit of asteroidal spins for large asteroids that are close to 90 degrees. And explain why the prograde asteroids are much more numerous than the retrograde asteroids. So I think this bimodal, this dichotomy of large stuff in a sea of small stuff not only helps in understanding extreme runaway growth and maybe the course of the giant planets, but seems to fit the spin distribution of the largest asteroids. And this is Johansen work. Unfortunately, it's not here.
Okay, I think we need to move on now. Let's thank Morby again.